request Dr. Anand to let him be heard.
Good evening, Ananda. Welcome to this gathering. Today we are having the third lecture in the series of ASI POEC. So as you know, this public talk is organized on the occasion of 42nd meeting of ASI, Astronomical Society of India, and a series of public lectures has been arranged here at Jawaharlal Nehru Planetarium as a POC public outreach and education program. So we are here for the third day public lecture. So on this occasion, we have Professor Durgesh Tripathi with us from IUCAA. So I kindly welcome him with a bunch of flowers. Okay. So I request our Administrative Officer K.P. Rajan to hand over the book and formally welcome him. And as a token of gratitude and our love, we would like to present a memento to the speaker. Also, I welcome Manodolf for this lecture. So, I'd like to request Dr. Bengaluru to introduce the speaker.
Good evening, everybody. Thank you for showing up. So, I am Bengaluru. I am the chairperson of the Public Outreach and Education Committee of the Astronomical Society of India. So, we are having the 42nd meeting of the Astronomical Society of India in Bengaluru. It's a scientific meeting. On the sidelines of it, we have a series of public events planned throughout the week in Bengaluru. And you may have seen the program that we have had in various parts of IUCAA Planetarium especially throughout this week. And we have two more lectures coming up this weekend, Saturday and Sunday, one on the Astro mission and the other on the Himalayan night skies from Ladakh by Jawaharlal. So today we have Durgesh, and it's a pleasure to introduce him because we are almost contemporaries and known him for a very long time. So Durgesh did his PhD in solar physics from Max Planck Institute for Solar Physics in, that time it was in England, Germany. Following which he went to University of Cambridge at the Department of Applied Mathematics and Theoretical Physics to his postdoc. Following there, he moved back to India, assumed the professorship at the Indian University Center for Astronomy and Astrophysics, where he has been ever since. So he is a quite renowned researcher in the field of observational solar physics. He has won the Moody Foundation Award in Plasma Physics from the Physical Research Laboratory. He's won the Group Foundation Award from the Romanian Academy of Sciences for his work on the origins of solar magnetic storms, which I hope we'll touch upon today. And he's also the principal investigator of the Solar Ultraviolet Imaging Telescope, which I'm proud to say is the first space-based instrument from India to have observed the sun and taken images of the sun. And hopefully today you will see some of the first pictures of the sun ever taken with an Indian space-based satellite. So without much ado, I welcome Durgesh to the stage and take it away. Please.
Thank you very much, Aditya, for that introduction. And also, thank you as a POEC chairman to invite me to give this talk and share the excitement of having observed the sun with our own instrument from space. It's a pleasure to be here, and giving a public talk is one of the things which I really enjoy having headed the IUCAA Public Outreach Committee for about 4 years, I got into this and I really love it, and so I'm looking forward to share the excitement. Now, because we're going to talk about the sun through the Aditya 1, its own eyes, so let me start with that, and I'll show you the first image taken by our own instrument on Aditya 1. So this is one of the filters, and this is the Solar Ultraviolet Imaging Telescope, which is now on board Aditya 1 and is regularly, continuously, 24/7 observing the sun and providing data in different filters, mapping different heights into the solar atmosphere. Now the question is, that's a nice picture, photograph, and we also know that the sun rises in the east and sets in the west, right? So it's nothing more than any bread you might think of, right? So bread also rises in the east. It's a different kind of east though, and sets in the west, right? So if you're all interested in that, and just the solar physics is over. But then you have to behave more like an inquisitive child, like Kelvin. You know the cartoon Kelvin and Hobbes? And he keeps asking questions to his dad and his teachers, the nastiest question ever, but they're very, very inquisitive. And one of the fine days he asks his son, why does the sun set? And it's a very profound question, right? And his father tells him, well, it's because the hot air rises, the sun is hot during the day, so it rises and it cools down and it sets. And then he says, but then why does it go from east to west? Right? And then he said, well, the wind also goes from east to west, so the sun goes with it. And that's where he gets completely confused. Right? So one has to do astronomy, and you have to be as inquisitive, if not more, as Kelvin, to get into deeper and deeper physics questions you ask. Right? So, having said this, let's put the solar physics in general perspective, right? So that's again coming back to the sun, and let's put this in a little bit of more global and general perspective. Where does the sun stand, and why do we really care about the sun and launch a space mission to go all the way 15 lakh kilometers at L1 and worry about the data which is coming and trying to analyze it? So that's the whole thing about the talk, right? Now, you must have seen this picture in the newspaper, online media, and all that. This is a picture taken by James Webb Space Telescope, and there is a reason that I'm showing this here. There are other nice pictures. Remember that this is at the second Lagrange point, and I'll come back to it and I'll tell you the significance of it. In this picture, what you see, all these dots, right, tiny dots, are one single galaxy, right, like our own Milky Way. All this bright one here, this one is a star. It is too bright, it just beat the detectors and so on. But all these points you see here, they're one single galaxy. Then so what? When you look at our own galaxy, in the universe, there are about 100 billion galaxies, and our sun is one of the 100 billion stars in our own galaxy. Right? So this is an artistic impression of our own galaxy, and this is of course artistic because you cannot take a face-on image of your own galaxy, because the galaxy cannot take a selfie. Right? You can take your own image because no selfies there, but earlier you couldn't do that. Where do we live in this galaxy? We live in an area which is very, very quiet. Something like we live in the suburb of Bengaluru, where all the activities are happening at MG Road, right? So at the center, from the galactic perspective, all the activities are happening there, and if you have to point where JMP is, it would be somewhere really far away from the center of the galaxy. Right? So from the galactic perspective, it's kind of a place where you should not really bother or you do not really bother, but then it is important from the perspective that it has its own family, and this family is us. Right? So you have in this family, you have the star, which is the boss of the family, and we have all the other planets, we have asteroids, we have comets. This planet, it used to be a planet, Pluto, but unfortunately the International Astronomical Union made a decision to take it out. Now, that doesn't belong to this particular planet family, but it still is a part of the solar system. And this also has us, because sun sustains life, and we live because the sun lives. Now, whatever we do, this was supposed to be an animation, this doesn't work. It's important because we live here, and the surrounding and the environment which is provided to us is by the sun. We cannot control it, but rather we have to safeguard ourselves for whatever purpose and whatever way we want to live. And considering that our life is much more dependent on technology, and particularly in India, we are a developing nation, and we want to do as much as possible and develop technologies as much as we can. We are fully dependent on what the sun does and how it shapes the geospace and how it shapes the geoclimate and space weather and so on and so forth. Okay, now it's not that we are starting the sun's observation now. The sun's observation has been done historically and even in old literature and all that you know. Here is an animation which is put together by taking Galileo's original drawing, and is considered that he was one of the first ones, to point a telescope at the sun and look at the piece of paper and view everything precisely and consistently every day, and to look at what the sun was doing. And it says there, black spot on the sun, and it also says that it went from is settled by the side of the sun. So it talks about going from one side to the other side. So this goes much earlier than what Galileo had talked about with it. Sense of what the size of a sunspot could be, right? So if you take one of the bigger sunspots, there are multiple sunspots very often. The bigger one could be as big or even larger than the size of the Earth you could have. So these are really huge structures on the surface of the sun when you look at it. Now, because the sun is close by, you can do more observations and you can do quite fast observations, and you can start looking at how does it vary. Earlier we talked about daily variations when Galileo looked at one image per day. Now we can look at a time cadence of every 10 seconds or even a few seconds in a day, and then you look at the time evolution of these structures itself, how do they evolve. And if you do that, this is what you see. So this is taken from a Swedish solar telescope. This is a ground-based telescope, and what you see here is a sunspot which has nice structures which are flowing out of the sunspot, and what you also see here, these are the bright blobs here, there are dark lanes in between, and these are all, they're nothing but giving you a sense of convection cells. You know, the heat is produced inside the sun because of nuclear fusion, the energy is radiated, and then eventually it's getting convection. And convection is nothing but what you see when you boil water in your kettle. So that's how the heat is transferred from the center all the way to the surface, and that heat does not penetrate here in this area, which are sunspots, and that's why their temperature becomes lower and it becomes darker. Now, why does the heat does not penetrate there and darker? Because there is a very strong magnetic field. So the magnetic field is generated inside, is coming in form of sunspots, and they block the heat to flow through, and that's why it doesn't come up, and then you don't see the heat radiation coming out from this heat. Okay, when you look at these sunspots, as Galileo did, he did it every year, and here what you see, there are two images which are taken apart, 2001 and 2005. At one point, you see that there are many sunspots. Of course, they are located in these two bands, but if you look at it after 5 years, you have absolutely no sunspot on the surface of the Earth, surface of the sun. And now we know that it has a sort of cycle where the sun starts producing sunspots from 0, keeps increasing, goes to maximum and comes down, and that's what we see here. If you just count the number of sunspots per day and put it in a plot like that, so this is year-wise, this is, for you, this is just number, and what you find is that there are times when there are no sunspots, and that increases, goes down, that increases, goes down, increases, goes down, and this is what is called sunspot cycle or solar cycle. And that you can see this happens every 11 years, and that is what is called solar cycle of 11 years. Now, this is getting a little bit more detailed. You want to do physics, you just don't want to count. So, as a physicist, you also count, okay, where do they appear? Do they move in some certain way? Or there is some pattern for their evolution? So, what you do is just define some coordinate system. Here we call 0, 0 here, 90, minus 90, plus 90, plus 90, minus 90, and so on. And you can put that together in a similar way, and what you see that this shows the butterfly pattern. Right? That is what your butterfly pattern. The sunspots start appearing, they move towards the equator, then they jump out, they move towards the equator, jump out, as if a butterfly opening the wings and going out and flying away from you. So that's why it's called butterfly pattern. Now, I told you that there is a magnetic field, and that's why it is darker. How do we know? We can measure magnetic field from space, also from ground. So this is done from solar. So this is your good old sun. Take an image of the sun with a normal camera, for example, and you see there are sunspots here. Now, at those positions on the sun, at every point, you can measure magnetic field, and you find that there are magnetic fields here. So these are magnetic field map. At each point you see, it tells you the information about magnet. So the dark here tells you this is the south pole of a magnet, and the white here tells you the plus side of a magnet. So if a bar magnet, you have a dipole, plus and minus. So you can imagine that the surface of the sun is, you have spread it over so many bar magnets, is showing plus and minus, and so on. And now we can do this, and you can also see that there are magnetic field stronger, so that the brightest and darkest region tells you the strongest and weakest magnetic field, right? And the plus and minus. And here the gray means roughly 0 magnetic field. Is it really 0? If you can do with the better measurement, what we find is that, of course, you have two belts where you have two sunspots appearing. You have these magnetic field is stronger, but anyways, so if this doesn't want to work, there was a switch of the computer, and that's scared the whole thing. So if you realize that the sun's surface there is no 0, there was always black and white patch. Here. And it is like a pizza, that on the surface you have these really stronger ones, and then it's filled over all these salt and pepper everywhere. And that also shows, if you measure magnetic field, as you look at the magnetic sunspot numbers, it shows a sunspot cycle of years. Now, why am I telling you all this? So, I told you now that at the center you have this nuclear burning, and on the surface you have the radiation, you have the convection, and then you reach onto the surface. And at the center, to start nuclear fusion, you are talking about a temperature of about 15 million degrees. And of course, when you're going away from the heat source, you are going to feel less heat. Right? There is a fireplace, you're going away, you feel colder and colder as further you go, and that's what happens, that if you reach on the surface, then you reach a temperature of about 6,000 degrees. Okay? Now then, what happens is that if you change your filters and all, and you take a picture of the sun in X-rays, right? So here is the picture of the sun from ground or from space in visible light. If you take a picture of the sun in X-ray, what you find is there are really regions where the sunspot, which looked darker on the surface, in X-ray images, these are the regions which are looking really bright, right? So that means we are emitting radiation, emitting light in X-rays very profoundly. Right? Now, if something is emitting in X-rays, the gas which is there has to be a temperature of more than 1,000,000 degrees, right? So remember, this was the surface, this was 6,000 degrees. On the center, we have the nuclear fusion, we have 15 million degrees. And now when you take an image of the sun in X-ray waveband, which is mapping the upper layers of the atmosphere, you are getting 1,000,000 degree or more on the surface. As if you're going away from this wall and suddenly get hit by a wall and you don't see where it is. Right? And that also shows, like magnetic fields, you have this stronger magnetic field going to no magnetic field and stronger, so that in a cycle, this atmosphere of the sun, which is showing X-ray radiation, that also varies as time goes by in a million years' time. So now you can see that the whole thing is coupled by the way the magnetic field is behaving, because magnetic field is deep inside, generated, comes up to the surface, it shows you dark sunspots, but the same magnetic field which is going higher up in the atmosphere, it shows you these bright stretches. Right? So how and why does this magnetic field does this dirty work of creating somewhere darker stretches, somewhere brighter stretches, and the interplay of the magnetic field and the gas is something which people want to understand. So let me just bring back to this. So your surface is around 6,000 degrees. It is full of bit of hydrogen on the surface. You get helium, calcium, iron, sulfur, all the elements on the surface of the sun. Right? And that is why it's called that we are all stellar material. Okay? Now, from the surface, you're going out into the atmosphere. The further away you go, the higher the temperature you reach. And that's what it is. So here, 6,000 degrees, about 1,000 kilometers above, you get about 20,000 Kelvin, and then you get about more than 1,000,000 degrees. Right? This is just showing a plot that on the surface you keep walking uphill. To some extent, you will feel less change, but then in about 100 kilometers, the changes are so steep that the temperature goes from about 20,000 degrees to 1,000,000 degrees. Right? And that is what has bothered the astronomers in general to try to figure out that why this could happen. Because this actually questions the basic laws of physics. That how actually you can explain this considering all the thermodynamic laws are working. So this is the fundamental physics problem. How can the regions be hotter when they are further away from the heat source? And now we know that this is done because of magnetic field, but how does the magnetic field do it is something, a question we are bothered. Now, this is a basic fundamental question, but how does it affect us? And it affects us by the way that at such high temperatures, if there is a gas at such high temperature, all elements are ionized, and we have gas of ions and free electrons. So what? It starts to produce radiation in the wavelength which we don't really want. It starts to produce radiation in X-rays and ultraviolet. Right? It doesn't come to us because there is an atmosphere of the Earth, but if it wasn't there, it wouldn't have bothered us. So this is undesirable radiation part of the sun which we don't want. At the same time, we want the good thing from the sun, but the sun also gives you something which you don't really want. And in addition to this radiation, that's just light coming in, because it is a 1,000,000 degree hot plasma, everything is fully ionized, we have all these energetic particles, and the sun then starts streaming all these energetic particles into the interplanetary medium, towards us and beyond. And as I said in the beginning, that you do whatever, you have to live in the environment which is provided or defined by the sun. You cannot do anything to control that, but you can do many things to protect yourself. But to do that, you really need to understand how and why the sun is doing this. Now, if you take the image of the sun, because now we know that there are various frequency photons and lights are coming, you can image the sun at various wavelengths. And this is done by Solar Dynamics Observatory of NASA. So this is your sun, which we talked about earlier, and then you go higher into the temperatures, that means you're mapping at different layers in the atmosphere. You can see that depending on what frequency of light you are taking, the sun could look very, very different. However, one thing is very, very common, and as you can see, that look at this sun spot here, that's the region here, that's brightest here, it becomes brighter, and it becomes brighter in the upward. So the same magnetic field which is generated deep down is connecting on the whole atmosphere. Okay. Now, when this radiation is just going towards you, what it all does? What it does is, so this is the radiation band from the sun coming, the X-ray, extreme ultraviolet, far ultraviolet, near ultraviolet. You know, the physicists like to divide things in narrower regions to try to understand this. And what you see, that depending on the wavelength of the light the sun is changing, different part of the Earth's atmosphere absorbs different frequency photons. And as you can see, here X-ray comes to the mesosphere, UV, thermosphere, far UV, thermosphere. This middle and near ultraviolet comes all the way up to the stratosphere, and some comes into the troposphere, and also a little fraction of that comes onto the surface. Right? What it does, if you put light to a gas, the gas gets heated, right? Because this radiation is bringing energy, that energy gets absorbed by the atmosphere of the Earth, which is also gas. Now, when you heat the gas, what happens? The gas expands. Now, when you cool it, the gas shrinks. Now, imagine that the sun is putting this radiation, and that also has a variation time period of 11 years. Now, it is putting energy into the Earth atmosphere. The Earth atmosphere absorbs it and then expands, and then it shrinks when the radiation starts to diminish. So at every 11 years, the Earth's atmosphere does like this. Right? Now, you're very much worried about your navigation, you're very much worried about your mobile phones and television and all that, and any kind of observations you want to do from satellite in space. The satellite is doing nothing, but it's just floating and you have some control on it. Right? You try to make the satellite as symmetric as possible, but there could always be asymmetry in your satellite. Now you don't know where to put it so that it doesn't feel any drag forces which is provided from this shrinking and expanding system. Now you put it here, it's just floating, and the gas does this. It will go down and expands, it will go up. Right? You take a balloon and blow. What will happen? It just keep going up and down and it's vibrating, right? And if it is not a symmetric one, then it can just topple over, right? And you lose your satellite. So it has a very strong space weather implication of how this radiation changes. And mind you here that from solar minimum to solar maximum, when you have less number of sunspots and the maximum number of sunspots, the temperature in the Earth atmosphere changes by about 200 to 400 Kelvin. That is a huge change in the temperature, which will change the heating in the atmosphere. So expansion and shrinking and leading to unwanted forces on satellites. What else happens? This mid-UV and near-UV comes all the way into the stratosphere, and that is where you have your ozone layers, right? And you have oxygen molecules. How does ozone forms and how does the oxygen dissociates to combine with another oxygen molecule? It's all decided by primarily how much radiation or the ultraviolet photons are coming from the sun and getting absorbed by these oxygen and ozone molecules. And they play as a catalyst to dissociate the oxygen and also dissociate ozone and then deformation. So depending on how much radiation is coming from the sun, the whole chemistry of ozone and oxygen is decided in the Earth atmosphere. And the least part of this here, which comes all the way into the ground. You might have heard people going on the seaside with no clothing and getting skin cancer. Right? So that has very strong implication on that as well. In addition to that, you also have these energetic particles which are completely, always sun is bombarding with the earth, right? And that's the earth. Now you're sitting somewhere else and looking at the earth here, and these energetic particles, along with the magnetic field from the sun, is just coming and bombarding the earth all the time, 24/7. Luckily, we have this magnetic field on the earth, which will show up soon, which is just deflecting all these particles around this, and they are getting away, surrounded, and getting protected. Now, sometimes when the sun's magnetic field gets into direct connection of Earth's magnetic field, what happens? You put all these energetic particles in the Earth atmosphere, and sometimes you see these nice. There was supposed to be an audio in this. That's not the audio I was talking about, but you see this beautiful array. It's okay, leave it, that's fine, it's okay. And so this is taken from Norway, and you can see you drive around here, and you see this beautiful phenomena in this case spread over kilometers, and that happening is all the time, right? And imagine that if these energetic particles right? So these are nice phenomena to look at, of course, but this could have unwanted effects also, because these energetic particles then they're looking for conductors, right? Conducting mediums, and when they get into your electric pipelines, they go to transformers, and transformers are not built to look at NEV and GeV particles, and therefore you would burn your transformers. Now, having said all that you have a continuous radiation all the time, and then you have a continuous bombarding all the time of energetic particle in form of solar wind, you also have structures like these sitting on the surface of the sun, sitting there for months and months, and then suddenly one fine day they start to erupt and engulf the whole interplanetary medium with these kind of plasma and gas. So this structure is called prominence, and if I zoom in up and see that this guy is just sitting there and it just erupts and goes out, and it gives you this brightening on the surface, which we call flares. And this mass which has gone in, it was just fitting into the whole heliosphere. And how much of that comes in? The mass of one of these ejections could be about 10 to the power 15 kilograms. Now, it could be as large as 1/4 or sometimes up to one solar radius. One solar radius is 700,000 kilometers, right? And that is the kind of structure which is erupting and is getting pushed into the interplanetary medium and taking all this mass, which is 10 to the power 15 kilogram. What happens? 1,000 billion ton of mass is getting into the interplanetary medium and engulfing it. Luckily, the space between us and the sun is vast, that these structures will expand, and if at all, we get a very tiny bit of it. But that is enough to create havoc in the space weather. Okay, I think it did work for a while. Okay, let me see. That doesn't want to work. Fine. So we talked about radiation, we talked about the particles. So 24/7 radiation, 24/7 particles. The radiation has a solar cycle of 11 years. The particles will have a cycle of 11 years, of course, as well. And we have these eruptions which are given, and that also is related with what the magnetic field and how the sun is working. So what do we want to learn, right? Because if we want to look at all these implications which radiation has, and we have to understand it, then eventually we have to go back and try to understand that how the sun manages to produce this radiation, and then if we can measure how much is coming, we can predict that how to actually safeguard our navigation satellites, the space weather and so on. At the same time, it will help us understand this fundamental question that how does sun manage to produce all this, right? So that's a comprehensive view of looking at the sun and heliosphere, if you like, the sphere around the sun is called the heliosphere. So let me summarize what I have told you so far before I go ahead. So we have electromagnetic radiation. It has, so electromagnetic radiation, that means X-rays, ultraviolet, visible, infrared, and so on. It has long-term effects, satellite drag, oxygen, ozone, chemistry in the Earth's atmosphere. And we want to sort this out. That means we want to understand the origin and variation of this electromagnetic radiation on the sun itself. Right? And that eventually can help us understand that how did the sun manage to give this million-degree plasma, which is the fundamental question. Now, on the other hand, we have the solar wind, which is charged particles have been happening all the time, and that happens because the plasma is fully ionized. So we want one, and it has also auroral effect, and we have space weather effects. On top of that, you have these sudden large-scale eruptions that also puts in charged particles with magnetic field into the Earth's atmosphere. Now, to understand all this, what we need is to understand the origin of large-scale eruptions and then properties of these charged particles. And these both then bring back to the same question that how does sun manage to produce this 1 million degree plasma to begin with. And therefore you are talking about looking at the fundamental physics problem, at the same time its implication on how and really the sun-climate relation is governed by the way the sun is working. And therefore, one has to go to space and continuously monitor the sun and its activities that has to happen 24/7, because you don't know when the sun is going to produce this large-scale eruption. And it is continuously producing all these charged particles and so on, so you have to continuously monitor it all the time. And that is why ISRO, a lot of space missions have been interested in it, and ISRO has got into this and given us the opportunity to launch Aditya 1, and hopefully this will work. So that's the launch. There was an audio that tells now Aditya 1 goes to space, or the spacecraft, the rocket goes to space taking Aditya 1, and that's how this was there. We were there to witness it. Professor Nandi was there with us, and it was a lifetime dream for any scientist who's working on this to actually see when you have spent 10 years at a time, something goes up there and it starts to work. And it was fantastic. And once it is launched, on 2nd of September, the rocket went, and all your 10 years of life has turned into fumes. That's what you had, because what you built, it just went, all you are left with fumes, till the instrument starts to send you the data back. Right? And that's one of the data which I showed you, the instrument sent it back. Now, what is Aditya 1? And this was after the launch. A different instrument had different PIs in the control center at ISRO, and this is where everybody was happy, at the same time feeling a bit nostalgic that all our work has gone into space. No, but let's wait and see what happens and so on. So Aditya 1, that's the satellite. Which is flying now at L1, not the trolley. Trolley was just there to move it to the clean room. And it is located, or it is orbiting around the first Lagrange point. And remember, I started off with showing an image by JWST, which is at second Lagrange point. Right? Second Lagrange point is a region where you want to take the energy from the sun because you want to charge the solar panels, but you want to block everything behind the Earth so that we start looking into deep space, night sky. But for sun, L1 is the location because you will always want to look at the sun. And when you put a satellite at L1 is a point, or all these 5 points are points where the gravitational effect or the pull from the two bodies becomes negligible or nil. That means you put a space there, that should remain there. And if you put a satellite here, it just keeps orbiting around L1. And when this is the Earth, it goes around, the L1 point also moves around, and therefore the satellite starts going around the Sun as if it's not a satellite, it's a planet, because now it is going around the Sun, not going around the planet, around the planet itself. So Aditya L1 is going around the Sun, and because there is nothing in between L1 and the Sun, it takes a continuous 24/7 observation and sends the data back to Earth because it's always in Sun outline. So that's how the trajectory was, and you might have seen at the entrance of the planetarium there was a beautiful the show where it shows how the orbit was and how it was injected into the L1 orbit. So this is the Earth, it went around, gets some speed, then it exit in, and then you have the insertion at in the L1 orbit, and that's when it was inserted on 6th of January. If ISRO did not capture it, then it will just fly away in this path and go somewhere else. So it has to be very, very minutely done, minutes, because you also want to save as much fuel as possible to bring it into this perfect orbit so that it goes around and start giving you the observation. Now it has 7 different payloads, and all my slides got completely haywire here because I have to change the computer, but you can count there are 7, and there are 4 instruments which are looking at different kind of light, so different frequency lights. As I told you, there are all kind of lights coming from the Sun, and 2 instruments which are looking at different kind of particles which are coming in the solar vent. At the same time, I told you when the magnetic field of the Sun is in connection with the Earth's magnetic field, you put in all the charged particles. Can we say that when does that happen? And it appears that when the two magnetic fields are in the opposite direction, then you have a direct connection to the magnetic field. If we can measure that, then we have some ways of saying, okay, this particular eruption is going to put in all these energetic particles in this space. And that is why we have this magnetometer in this space. So we are covering the radiation band all the way from X-ray to infrared. So almost the whole electromagnetic band, plus these 2 energy ranges for energetic particles and magnetic field. This is one of the most comprehensive satellite ever flown for solar physics worldwide. So that gives a complete physical understanding of how the Sun works. These are some of the images. So here is the satellite. This is going into vacuum chamber because you don't know what the conditions are going to be there. So you make your instruments to a level that it can take all kind of extreme temperatures, cool, hot, vibration, everything, all that testing you have to do. And that is why it is hanging there and getting into the vacuum chamber and so on. So all these tests are done at ISRO. This is the instrument which we built. This is called Solar Ultraviolet Imaging Telescope. Of course, we led it from IUCAA, and a lot of integration and things were done at ISRO, but our collaborating institutes, this is Manipal, IIA, PRL, and the Center for Excellence in Space Science India at IICAA Kolkata, which is led by Professor Nandi here. So we had a sort of national collaboration with various institutes and with ISRO, and we built this solar ultraviolet imaging telescope and put it up here, that is sitting glorified on the satellite deck with a door here in front, which will look at the Sun, open the door, and give you the solar observations. Okay, let's see. So, this should have not come before. Anyways, so the instrument was switched on November 20th. At least one of the instruments. All the instruments have been switched on. They're all working perfectly. And I'm going to tell you more about one of the instruments which we built, and I'll show you some data which we have taken. The door of that was open. This doesn't want to be shown. So this thing here is taken, so there is a camera on the satellite itself, which is looking at this door, and when the door opened, it took an image of the animation of the door opening, right? So the door opens, and then you see this first light image of the sun, right? And all the features we talked about, sunspots and brighter regions and these quieter regions, all this have been captured with glorious details, which we anticipated the solar ultraviolet images telescope to do. And as I said, because we want to measure at various heights, because the magnetic field which is coupling the whole thing, we want to understand that how different layers in this brightening is all is coupled. And as you can see, there are sunspots here in different bands you can see, and also these brighter layers and so on. So we have 11 different filters which is slicing through the atmosphere and giving observations of the sun's atmosphere. On the day when we switched it on and started taking data, this is what we observed. This is only portion of the sun, and look at this thing here. As I showed you earlier, taken from other space missions, the thing was sitting there and it started erupting. Here it shows something beautifully danced structure, right? So you see this structure is just sitting there dancing, and then eventually, finally erupting. All these things are coming because of the projector issue. Now it is not, I can show you. But we also take various images in different filters, some are smaller and also full disk. Here is only this part is shown in all 8 other filters, and it's showing you how these structures are looking different. And now it's time to look at all this data, to look at the physics of this, that how all of these are captured and combined. Oh, this projector is nice. It gives time to the speaker to actually read, which is nice.
Is there a movie that you're waiting for?
No, I'm just trying to switch it to go to the next slide, and somehow it's probably because the talk is very heavy with the number of information and all that. So.
I think it's not a problem of the projector. Probably the laptop needs to have had it.
It could be possible, yeah. No. Let me see. I don't think there's any issue with that. No, this should work from here now. There is nothing to do with that. It's just this. No, it's not working. There's just some issue with that. Anyways, I was almost at the end of my talk. I have 2 more slides to show you some videos. If that works, we can show it, or this is also the right place to stop because it's been almost an hour. And what you see here, we are now producing this data 24/7, and the instrument is being calibrated. Number of testings are being done, and we are looking forward to doing different kind of science, which is commonest to propose. No, it's not escaping. It's a random sheet. It's an old laptop. Okay, I'm happy to take questions. Thank you very much.
Any questions?
I'm not educated with this. I'm a general person. So we understand maybe there is a balancing between L1, L3 and L4. Is L2 and
L2 and L3.
L3 are opposite and outside.
Yes.
So can you talk about that? Because our understanding doesn't help us to say how.
Right. So because if you think of it, only two bodies are attaching among each other, right, and pulling towards each other. That's where the gravity force will work. But it goes a little more complicated when you think of the space-time structure, right? So if you think if there are two bodies and there is a space-time, right? You have a very heavy body which is pulling this space below, and there is a lighter body which is pulling only up to this much, right? So now, because we have only two bodies, then between this, there will be a place where neither this will pull, neither this will pull. But at the same time, on the other side, you have this fabric which is also being pulled. So there will be a place where this equilibrium will be balanced when you put some fabric there, right? So and then you have to add a three-body system because it's not the sun and earth there. So that the space-time curvature becomes very different, right? At the moment we think in only in two vector times, right? But the force is a vector, this is going this way, that is going this way. So why there are other points? Because there is only one sun on planet, right? And one should be the point. But it was done 1800 something by Lagrange, and he was a French mathematician who actually looked at all these three-body problems and tried to figure out what these points could be.
Any other question?
Wow, it's the youngest member. Don't ask me tough questions like Kelvin, I don't know.
What was the NB something?
Oh, NB, oh yeah, that's a good question. So NB is just a name we gave to that. It's called narrow band 1, narrow band 2, because when you design a filter, you take photographs. You like it? Yeah? Okay. So then you go home and ask your parent to buy you an H alpha filter. H alpha filter. So what it does is, the sun is giving a rainbow. You know rainbow now? So it's giving you 7 different colors, right? So each color has a different frequency, right? So you design filters to only pick out the light in a given frequency, right? So you only observe red, only observe blue, only observe yellow, right? So this is what we are doing. The sun is also giving all these lights, and we are using those filters to pick out only those photons which we want. So we define a very narrow band kind of filter. Filter meaning what? You have this much and I filter, right? Let's say grain. Big grain is small grain. I only want a small grain, so I use a filter, only small grain will go up. Right? So I'm using a filter only to light that pass, which I want, and rest is get reflected. Okay? So one of them is called NB1. Then I do another one. So I call NB2. And that is how we have named them. Okay? Oh, the slide has come. Okay.
But it has again a problem because maybe the size of the images are
Possible. Let's see if it does. It's okay anyway. It doesn't work. It's a problem.
Don't sweat over it. It's okay.
Yeah, that's fine. Okay.
Any other question?
Yes.
Why light not travels in a straight line?
Light is not traveling in a straight line. Yeah, that's very, very difficult question to answer. But anyway, let's see. Let's say if the light is going from here to there, it is straight, right? If there is nothing else around, it will go straight, right? But if there is a very heavy body here, right? Then because of the gravitational pull. You know the gravitational pull, anything is attracting towards each other. So that body will attract this light also. So it will go towards that body and then move like this. If you're talking about a black hole, then everything will go inside, you know, because that's the heaviest. Right? But if you're talking about any other smaller body, it will just go in there. That's called, that's how the space-time curvature is defined. And Einstein came into all this picture. Right? Oh, these two kids are like Kelvin. I really love it.
Any other question?
Okay. Thank you very much.
So on behalf of the Astronomical Society of India, I have a little memento for Durgesh. This is a mug. This in fact has the first image of the sun taken by the instrument Solar Ultraviolet Imaging Telescope, of which he is the PI. So I borrowed the image from him, put it in a mug, and this is a gift that we're giving to all our public speakers. So Durgesh, it's my pleasure to give back the image to you. Thank you. Welcome.
Wow, this has come out really nice.
Yeah. Okay, I'll put it in the back. I'll give it to you later.
So, if there are no more questions, then we can come to the last stage of the talk today. So now, I'd like to take the opportunity to propose a vote of thanks. So, firstly, I would like to thank the speaker, Durgesh Tripathi, for taking us on the solar tour. It was really a wonderful concert. And